Alright, ladies and gentlemen, welcome back to the second session of our class. So in this session we're going to look at some problems based on what we did in the previous session. So now here we're going to focus on some of those examples on work, energy, power, potential. So we'll start with work. So I've opened up a folder here, or rather a document here, and we have a question here, the second question, as you can see. So the question is, what work is done by a force F? Okay, the force is given F, which is equal to 2x newtons in the I direction plus 3 newtons in the J direction plus 4z squared newton in the K direction, with x and z in meters. So they've given us x and z are in meters. So now this particle moves from a position Ri. So this is the initial position. Ri equals 2 meters in the I plus 3 meters in the J plus 4 meters in the K to a position Rf, meaning R final. So this is a vector position, the final position Rf, which is equal to minus 4mi minus 3mj minus 2mk. The m's are just representing meter. Alright, so this is our question. What work is done by this force given this initial position and this final position? Okay, so let's look at our solution now. Let's look at how to solve this problem. So here we are looking now at the solution to this problem. As you can see, this is our example 1 there. So now last time we saw in the notes here, we saw that work there, you see, we saw that work is equal to F dot dr, right? The integral of F dot dr from Ri to Rf, or R1 to R2, which is the same as R initial to R final. Alright, now looking at what we have here, we have the formula, the same formula written: work equals the integral from R1 to R2 of F dot dr, which is the same as the integral of Ri to Rf of F dot dr. So here is our question: what is work? As I've written here, I've left it deliberately with a question mark. So now we're going to look at first the general way of getting these forces and the dr vector. So generally, force F is equal to fxi plus fyj plus fzk. So this force F should have a component in the I direction, right, which I've written as fxi, plus a component in the y direction, which I've written fyj, plus a component in the z direction, which is fzk. And the dr vector is always this vector written here generally. As you can see here, I've written dr is equal to dxi plus dyj plus dzk. Now let's start by taking the dot product of f and the dr vector. So as you can see, this is our dr vector here. That's the general way of writing it. Now if we take the dot product f dot dr, so I'm just taking this thing inside the integral. I'm taking the dot product of this thing inside the integral on this part here. So f dot dr, we have this f here and this dr here, which is going to be equal to fxi plus fyj plus fzk dot dxi plus dyj plus dzk, that. So taking the dot product, we all know how it is. We take this fx multiplied by this dx, we get this fx dx, and then we take this fy multiplied by this dy, we get fy dy, and then we get fz multiplied by dz, we get fz dz here. You see that? Now we have this. We can now take this inside the integral. This f dot dr is just this part we took, so we can put it back in the integral now. Here we can therefore say that work is equal to the integral from ri to rf of f dot dr. So taking our f dot dr here, which is this, it will just be f x dx running from xi to xf. Okay, so I've just taken this first part here. Fx dx is this part, fx dx. Now if you look at our integral is with respect to what? With x. So now I take the component in the x direction, which is xi, which is x initial to x final, plus the integral of what? Of this fy dy, which is this part, the second part here, which is fy dy, the integral from yi to y final. Okay, from yi, which is the initial position in the y, to the final position in the y. So that is fy dy. Because it's with respect to y, as you can see, it is with the dy. That's why our limits are also going from yi to y final, plus the integral of fz dz, which is this part here, fz dz, running from z initial to z final. Okay, so this is the general expanded equation for our case. Okay, so rather this is the general expanded equation. This equation here is the general way of finding work done when you are using the formula of the integral of f dot dr. When you use this formula here, you have to use this way of calculating the work done. Alright, now for our case, we'll have work equals xi to xf of 2x dx. So you see, for our case, we have our x component of force is just 2x. As you can see in this question, it's just 2x here. We neglect the Newton because we don't want to deal with the units. We just want the value with its variable here. So we take 2x there. This is the component there. We get 2x. Okay, so as you can see here, we've got 2x dx plus 3 dy. Why the 3 here is because of this 3 here, these 3 newtons here. So we just take the 3, we neglect the unit. So we take the 3 because it's the component in the j direction or the y direction. So we just pick the 3 there and we put it here with dy there, running from yi to y final, plus the integral of zi to zf of 4z squared dz. 4z squared dz is our component of force in the z direction. As you can see from this general formula, fz is representing the component of force in the z direction. So we just pick that component and place it there. So this is fz squared. Let me just show you. As you can see here, we have 4z squared there, right? Yes, so just pick it and put it there. Now let's look at our limits here. Looking at this equation we've written here, let's now look at our limits. We've seen this is xi to xf, right? For this first part here, we're now looking at this first part. Our limits are from xi to xf. Now xi is representing the initial x position, and x final here, which is xf, is representing the final x position. Okay, so this part is representing the initial x position, and this part is representing the final x position. Now when you look at your question, look at Ri. Ri is the initial position, right? So if this is the initial position, it has got its initial position in the x, its initial position in the y, and its initial position in the z. And Rf is the final position, and it has got its final position in the x, final position in the y, and final position in the z. So our xi should be this initial position in the x, and our x final should be this final position in the x here. So our first part will have xi being 2. As you can see here, our xi will be 2, and our x final will be -4. As we have here, you can see our xi here is this 2 now, and our x final is this -4, and this part will return it the way it is, and we get this, you see. And then we say plus. Okay, so plus. Now looking at this part, have you seen our yi is here and our yf is there? So let's now go back to the question here and check for our yi and our yf. So yi is 3 here. This is just 3 meters, so we just pick the 3. As we did here, we just took the 2. So here we pick the 3 for our yi, and the -3. Since there's a minus here, we take the -3 as our yf. Okay, so our yi will be 3 and our yf will be -3. Okay, if that's the case, we get this. You see, we've taken yi as 3 and our yf as -3, as you can see here, and we get 3 dy as it is here, plus the integral. Now we have zi to zf, right? Zi to zf there. So now let's look at our zi and zf from the question. So this is our initial position. Now our z component is this, meaning that our zi is 4, and our zf going to this final position here, our zf will be 2, rather -2 because of this negative, so it will be -2. So we'll say our zi is 4 and our zf is -2. Hence you have this, we get 4 and -2, and this is the equation we get. This is what we're going to work with. So now from here you have to integrate each part. We integrate this part, this part, this part. So starting with this part for the x, integrating this part, we'll have this expression here. Integrating this, we'll have this expression. So as you can see, integrating 2x with respect to the x will just give us 2x squared over 2, as we have here, 2x squared over 2, with the limits running from 2 to negative 4, because here it's 2 to negative 4, plus 3y. Okay, why is it 3y? Because when we integrate 3 we get 3y. Yes, we integrate 3, it's a constant, we just get 3y, with limits running from 3 to minus 3, plus integrating 4z squared, we get 4z cubed over 3, as you can see here, 4z cubed over 3, with limits running from 4 to minus 2. We get that. So our work will be equal to this expression. Now this is just the simplified form of this expression. You simplify this, you get this. You simplify this, you get this. You simplify this, you get this. Okay. Alright, and finally, after punching this whole thing in the calculator, you get minus 102 joules. So this is our final answer, negative 102 joules. So there you have it. We've solved our first question here, and we've got negative 102 joules. Okay, all right. And okay, so now we can look at another example. We'll see this next example in the next session. We'll look at example 2, so hang on as I return to you.